Okay, we'll get into the Laplace transforms. We'll first look at the background, go into some simple transforms, look at inverse transforms, and then solve differential equations. So Laplace transforms allow us to convert rather complicated differential equations in the time domain into an equivalent algebraic equation relative to a different domain, in this case the frequency domain. This has useful applications in control systems such as circuits, stability, and transient responses, or mass damper systems and vibrations. So the notation we look at here is the Laplace transform of a function. In this case, the functions that we're all used to in case of time. And we get an output function, big F of s. S here indicates the S domain or the time frequency domain, and T here is the time domain. This is the formal definition of the Laplace transform. And there's an easy way of solving these using a table, which we'll get into later. But first, we'll look at some problems looking at the formal method using integration. So this first Laplace transform here, we have our function x of t is equal to 3. Imagine our x of t is our function here we input. So we can just plug this in here. So the Laplace transform will take on both sides. Laplace transform of x of t is equal to Laplace transform of 3. And we're basically just inputting that into here instead of f of t. So that is the integral from 0 to infinity 3 e to the negative st dt. Take the 3 out as a factor. Same integral, standard integral of an exponential, an e function. And that gives us this constant here, that's a factor of minus 1 over s, times our constant 3, gives us 3 over s, times our e remains the same from 0 to infinity. 3 is still there. And we plug in infinity first. So an infinity in the exponent, but it's negative, so that's 1 over infinity essentially, which is 0. Minus plugging in 0 here, e to the 0 is 1. So our answer is 0 minus 1 is negative 1 times a negative 3 over s. We get the Laplace transform of 3 is equal to 3 over s. Cool. Now the second problem is x of t is 2t. So same thing here. We'll take the Laplace transform of 2t, which is the integral from 0 to infinity 2t e to the negative st dt. 2 comes out. And in this case, we can do integration by parts. The substitute in u here. So u will equal to t, which means du is dt. Our dv is the rest, e to the negative st dt, which means v, the integral of that, is just negative 1 over s e to the negative st. And if we remember the formula, we get integral u dv is equal to uv minus minus integral of v du. So right now we're just solving for, we'll worry about the 2 later, but we're solving for this part here using this substitution. What that gives us is 2 just from here, and our uv, so u times v, negative t over 1 over s times t, or minus the integral of v du, minus the integral of v du. So we could just simplify this. 2 is still there. Just combining these. And we we got to remember this is still evaluated from 0 to infinity. This becomes a plus integral from 0 to infinity of 1 over s t. And I could just bring this out since it's a constant. Cool. Evaluating this first expression here, plugging in infinity and 0, we get infinity, let's see, let's write it out here. Infinity over s, that's irrelevant because we have infinity in the exponent, but it's negative, so it's in the denominator of the fraction. 1 over infinity is essentially 0. Minus, if you plug in 0 here, 0 for t, cancels out everything else, minus 0. And then we'll evaluate this integral here. Integral of negative e to negative st, you have the same factor, negative 1 over s coming outside. 1 over s times the negative 1 over s from this fraction here gives us negative 1 over s squared times e to the negative st. Evaluated at 0 to infinity. This cancels out, so we get 2 times negative 1 over s squared times e to the negative infinity, same thing, gives us 0, minus e to the 0th power, that's 1. Negative 1 times negative is a positive, so we get 2 over s squared. So that's pretty much it. So this all comes down to Laplace transform of 2t is equal to 2 over s squared. So those were the two Laplace transform examples. And that was using the formal definition with the integral. And we'll go into the table method. So this has already been tabulated for a lot of different functions. And this is a lot easier to do. So we'll first do the same thing. And because of the linearity properties of Laplace transforms, we can split this up, even though this looks long. So first of all, we can do Laplace transform of 2t. We'll split this up here. Minus the Laplace transform of t squared. I just brought this minus to the outside. Plus the Laplace transform of sine t minus the Laplace transform of 5. All I did is just breaking down this expression here. And we can just combine these all together. So Laplace transform of 2t. Go to our table. I just put in two tables here since the first one wasn't comprehensive, but we'll find what t is. So Laplace transform of 2t. The 2 is just a constant, so this is essentially the Laplace transform of t times 2. So if you look at this formula, this table here, right here, t to the nth power. So in this case, n is 1, t to the first power. And if you plug in 1 for n, 1 factorial is 1, s to the 1 plus 1, that's s squared. So the Laplace transform of t to the first power is just 1 over s squared. So that's the same thing as 2 times 1 over s squared. Laplace transform of t squared is the same thing. The exponent is just now 2, t to the 2, where n is equal to 2. So 2 factorial over s to the 2 plus 1. 2 factorial is 2 over s to the third power. So that is 2, I'll just write factorial just to be comprehensive, and s to the third power. Plus, so this is here, this is here. Laplace transform of sine of t. We'll go and find sine of t. Sine of t is here. Our a in this case is 1 since it's just sine of t. So we have 1 over s squared plus 1 squared since our a is 1. So Laplace transform of sine of t gets us 1 over s squared plus 1. Minus the Laplace transform of 5. This is just a constant. For a constant, it's just 1 over s. In this case, we're doing 5, so you just multiply by a factor of 5. The same thing as this times 5. Cool. So that is the final solution here. The Laplace transform equals to 2 over s squared minus 2 over s cubed plus 1 over s squared plus 1 minus 5 over s. And just to be consistent, each of these can also be solved formally using this integration, just like we did before. But now we're just using a simpler table method. Same thing here. The next question is t plus 1 cubed. We'll first have to just expand this just to make it easier. T plus 1 cubed. Same thing as t plus 1, t plus 1, t plus 1. Which is t plus 1 times t squared plus 2t plus 1, which is essentially the same thing as t cubed plus 2t squared plus t squared plus 2t plus 1. I'm assuming this is pretty simple for most of you guys. T cubed plus 3t squared plus 3t plus 1. So now you can see what I'm doing here. I'm just trying to get it into a form that we can find in the table. So same thing here, because of linearity, we can break this down into the Laplace transform of t cubed plus 3 times the Laplace transform of t squared plus 3 times the Laplace transform of t plus the Laplace transform of 1 t cubed. T cubed is using this power rule here where n is equal to 3. 3 plus 1 t cubed. That is 3 factorial over s to the 4th plus 3 times t squared. Same thing here. Now it's 2 factorial over s to the 2 plus 1. So 2 factorial over s to the 3 plus 3 times the Laplace transform of t. Same thing here, n is equal to 1. 1 over s plus s to the 1 plus 1. 1 over s squared plus Laplace transform of 1. Oops. That's just simple. Laplace transform of 1 is just 1 over s. So just to simplify this down, 3 factorial is 6 over s to the 4th plus 3 times 2 is 6 over s cubed plus 3 over s squared plus 1 over s. So that is the Laplace transform of t plus 1 cubed. So just like we have the derivative and the inverse of that as the integral, we can also go backwards. Right now we've been going from a function in the time domain, taking the Laplace and getting it into the frequency domain. And now we can just go the other way, take the inverse Laplace, and get the original function. So this first example, we have 6 over s, quantity s plus 3. And just before I solve any of this, I just want to see what this might look like. It looks something like this here. We have a factor on top and we have s squared plus a squared. But in this case, we have s times quantity s plus 3. That looks a lot like this form here, where we have a constant on top and s times s plus another constant, the same constant as the numerator. So let's try to get it into that form. So this is the same thing as, remember we wanted the constant in the numerator to be the same as the one in the parentheses. So in this case, we have 3 that's divisible in 6, so we can get the factor of 2 out here, times 3 over s times s plus 3. So this is the same thing, I just made 2 times 3 instead of 6. So now our f of t is equal to the inverse Laplace of our f of s, which is the same thing as saying inverse Laplace of this entire thing. We can take the factor out here, 2 times inverse Laplace, 3 over s plus 3. And that matches exactly our form right here, where a is equal to 3, and the inverse gets you this. 1 minus e to the negative at. So we get 1 minus e to the negative at, where a in our case is equal to 3. Don't forget our factor of 2, so that's 2 times 1 minus e to the negative 3t. We just plugged in back in a. And that is the answer for this. To make it clear, this is equal to our f of t. We're basically just doing what we did here, but backwards. We're finding our original function. So for the second problem, we have 2 over s times quantity s squared plus 4. Same thing here, we're going to look at the table, see what this looks similar to. We have quantity s squared plus 4. That looks like this. We have s quantity s squared plus a constant squared. And we know that this 4 can be rewritten as 2 squared. So we'll just rewrite that. Going back here, our a is the same in our denominator and numerator. And so this is our a here, 2 squared. And this is our a, 2. So this is good here. But it has to be a squared, just like here. And this is not exactly correct. This needs to be a squared. So what we can do is we can just force it to be 2 squared. But now that that's 4 and it was originally 2, we'll just attach a 1/2 factor here. So that 1/2 times 4 brings it back down to a 2. So this is now matching the form we saw in the table. So now we can just apply the inverse Laplace of 1/2 times 2 squared over s squared plus 2 squared. Bringing this factor out, and this form here matches exactly number 7, where the inverse is 1 minus cosine at, and a we concluded that it was 2. So our f of t is equal to, forget our 1/2 factor, times 1 minus cosine at, where our a is 2. So for this last one, we'll look at 20 over s squared plus 8s plus 116. And since we have a polynomial to the second power here, plus plus, this looks like we can get it into a form in the denominator that looks similar here, like number 19 here. Because we have a plus plus here, and we don't have a s plus a, we just have a constant on the numerator, we can force a perfect square in the bottom because we don't care about a constant. If we add 10, for example, we'll just subtract 10. So we'll focus on this one first here. If you want to get an 8s in this second order, you probably have to plus something, have to be a 4 in here, just to double check, that's 8, it's s squared plus 8s plus 16. Factor it all out. So since this 16, it was not in the original statement, we can just subtract 16 so that it cancels out. So we can rewrite this. F of s is equal to 20 all over s squared plus 8s plus 16 minus 16 plus 116. And that is equivalent to the original statement here. And this part right here is just s plus 4 squared. This part right here gives us to 100. Rewriting this, s plus 4 squared plus 100, which is 10 squared. And that gives us one step closer to that formula we saw on top. And let's go back to that table. So we have s plus a squared plus b squared, and that b has to be the same in the numerator, which we don't have here. We have a 20, but we need a 10. So this is our a, this is our b, and we need a 10 there. Same approach, we can just make that a 10. We'll just make that a 10. But to get it back to a 20, we just have a factor of 2 here. So that's pretty much it until we get the final formula is the inverse Laplace of 2 times 10 all over s plus 4 squared plus 10 squared. The 2 we can bring out, and this entire form here, 10 over s plus 4 squared plus 10 squared, is exactly this, number 19 here, where a is equal to 4 and b is equal to 10. So our original function f of t is going to be e to the negative at sine bt. E to the negative at sine bt, where a is equal to 4, b is equal to 10. So our final f of t is equal to, don't forget this factor 2, times e to the negative at, which is 4, times sine of bt, which is 10. There we go. So now we can look into solving differential equations. This is pretty much the application of these Laplace transforms. Just to look at the application, just to look at the notation of this, let's say x is equal to our function in time domain. The transform of x is x of s, and the next higher order derivative is s times x of s minus x of 0, the initial condition. And the second order derivative, Laplace transform of that, is s squared x of s minus s x of 0 minus x dot of 0. So you can see here that these derivatives, if you take the transform of it, it turns it into an algebraic equation, gets rid of all the derivatives. And that's what we can do in this first example. We have x dot equals to 3, and we're given our initial condition here. So we're solving for the initial function here. What is f of t, or in this case, what is x of t? So what you can do is take the Laplace transform of both sides here. Laplace transform of x dot is given here. S x of s minus our initial condition is equal to the Laplace transform of 3. If you remember from our table, transform of a constant is just 1 over s times that constant. So that's 3 times 1 over s, or 3 over s. Our initial condition here just plugs in. So we have s x of s minus 2 is equal to 3 over s. So now we just want to solve for x of s here. Move everything to the other side. Big x of s is equal to 3 over s plus 2 all over s. This is equal to 3 over s squared plus 2 over s. So this is now the same thing as what we just did in the previous examples, taking the inverse Laplace. We have our function in the s domain. Oops. Same thing here. We have our function in the s domain. And if we want to get back into the time domain, we just take the inverse Laplace of this. So our x of t is equal to the inverse Laplace of x of s, which is equal to the inverse Laplace of this expression here. 3 over s squared plus 2 over s. Using that table just again. So this first one here, 3 over s squared, this is one of those power examples we saw before with the exponent. So if our n is 1, we have the s as 1 plus 1, which is 2. This is where n is equal to 1, and that checks out. But we have a 3 over s squared, so that's just a factor of 3. So this 1 over s squared translates to a t to the 1 if you do the inverse Laplace. And then we just have the factor of 3 times that. So the inverse Laplace of 3 over s squared is just 3 over t, or 3 times t, or 3 times t to the first power. 2 over s, same thing. Now we have our denominator will have to be s to the first power, which means n has to be 0. So 0 factorial is just 1 over s to the first power, and n is equal to 0, which means t to the 0 is equal to just 1. So our inverse Laplace is of 1 over s is just 1. But here we have 2 over s, so that's just 2 times 1 over s. We know the inverse Laplace of 1 over s, which is just 1. So 2 times 1 is just 2. So that's pretty much it. The formula, the answer is x of t is equal to 3t plus 2. And this pretty much makes sense intuitively if you look at this function, as we all know, in the y-x plane. 3t plus 2, this is saying the rate of change, or the slope derivative, is equal to 3. Checks out here. And x of 0 is 2. So the y-intercept here is 2. And that makes sense there. For this final example here, we have x double prime plus 16x is 0. And we have these two initial conditions we can plug in. Same approach as before. We just take the Laplace of both sides. Laplace of x double prime plus 16x is equal to the transform of the right side, which is 0. Because of linearity, we can break it up into 2. Laplace transform of x double prime, we just wrote it out here. So this is going to be s squared of s minus s 0 minus x dot. Laplace transform of 16x, that's the same thing as 16 times the Laplace transform of x. 16 times the Laplace transform of x is just big X of s. Make sure there's a clear difference between these big x's here and then these small x's here. It'd be easier to see with y's or some other letter here. But we can just plug in the initial condition. Oh, forgot the right side. So the transform of 0 is just 0. And now we can plug in 0 here and 0 here. So it becomes s squared big X of x minus 5 times s minus 0 plus 16 big X s. Same as before, we're going to solve for big X. If we factor this out here, we have this term here and here. s squared plus 16. And what else is left? Minus 5s is equal to 0. Move everything to the other side. 5s divided by s squared plus 16. You can take the 5 out. It's the same thing as 5 times s over s squared plus 16. And what does this look like here? This looks like a... So we had an s in the numerator, which eliminates a lot of things, so we don't have just a constant like here. We have an s in the numerator, we have an s squared, and we can get a square here. Four squared is just 16. So now our final x of t is equal to the inverse of our our frequency domain, which is just the inverse of 5 times s over s squared plus 4 squared. S over s squared plus 4 squared. So a is just equal to 4. And the inverse of that gives you a cosine of a of t. So this gives us 5 times cosine of a of t, where a is equal to 4. So for our final solution, x of t is equal to 5 cosine 4t. And that's pretty much it. We solved for these initial value problems, these differential equations, translating them into an algebraic expression, and using the Laplace transform and inverse Laplace transform that we learned previously. We use the table method, which is an easier method, just identifying which variables here and expressions match these cases that are already tabulated. And we also just looked at the formal method with integration, is how you solve the Laplace transform.